Hi everyone, I'm Dr. N. Today, let me introduce the graph neural networks. Graph neural networks, or GNNs, are a class of deep learning methods designed to perform inference on data described by graphs. GNNs are neural networks that can be directly applied to graphs and provide an easy way to do node-level, edge-level, or graph-level prediction tasks. Deep Graph Library, or DGL, is a popular Python package built for easy implementation of graph neural network model family on top of existing DL frameworks. Currently, DGL supports PyTorch, MXNet, and TensorFlow operations. In this tutorial, we will learn about how to use DGL to classify node types using the famous Zachary's karate clap data. First, let's talk about Zachary's karate club. Zachary's karate club is a social network of a university karate club described in the paper An Information Flow Model for Conflict and Fission in Small Groups by Zachary. A social network of karate club was started by Zachary for 3 years from 1970 to 1972. The network captured 34 members of a karate club, documenting links between pairs of members who interacted outside the club. During the study, a conflict arose between the administrator, John A., and instructor, Mr. Hai, which led to the split of the club into two. Half of the members formed a new club around Mr. Hai, members from the other part found a new instructor or give up karate. This is a graphical representation of the social relationship among the 34 persons in the karate club started by Zachary. As you can see, the nodes are in two different colors representing the two social clubs those members belong to. Let's read the data set in CSV files. Here we are reading two files. One is the membership data, or node data. The other is the interaction data, or edge data. In this tutorial, we are going to treat members as nodes and interactions as edges. And the dataset takes age as a numeric feature of the nodes, affiliated club as the label of the nodes, so there are two labels, and edge weight as the numerical feature of the edges. You can take a look at the data frame for the membership. We have unique individual ID, and there are 34 members in total. We also have the club membership. An individual belong either to Mr. Hai or officer, denoted by 0 and 1 correspondingly. And also we have individual's age as a numerical feature of the nodes. Here we make a numerical column for column membership for plotting by networkx. And here is an overview of the interaction or edge data. As you can see, we have the source node, the destination node, denoting the information flow, direction of the flow, as well as the weights denoting the strength of the ties between the two individuals. We can use the popular networkx module to visualize the network. We import networkx as NX, and we can create a graph using the networkx module. Here we build the graph in networkx using the function from pandas edge list. We need to provide the data frame for interactions. We also specify the source and target, and optionally we can supply the edge attribute. Here is the weight. And we also need to set node attributes, and we set membership ID as the index, and we convert it to a dictionary. And we also set the nodes attributes using the set node attributes function in networkx. And then we can apply the draw function in networkx module. We supply the network graph we created, and we can also optionally supply define the node color as a function of club membership, as we have two clubs in this data set. And we can choose the argument with labels equals true so that individual membership ID will be plotted as well. And the resulting graph looks like this. As we can see, there are two clubs and 34 members in total. And now that illustrates how we can utilize the DGL library to build a neural network model on membership. Here we install the DGL library because we are going to utilize GPU, so we are going to install the DGL CU111, which is the current version of the CUDA installed in Google Colab, so that we can utilize GPU in the DGL computation. And we are going to import a number of modules for pre-processing the data. And now let's create a customized DGL dataset. The customized DGL dataset is a child class of the parent class DGL dataset. And first, let's define the constructor. In the init function method, we set the argument twin validation test split so that we can optionally decide how we are going to split the nodes into twin, validation, and a test set. And we inherit from the parent DGL dataset class by using the super method. And here we name the new graph karate club. And now we need to define the process method, which is required by this customized DGL dataset. We first need to specify how we are going to get the nodes data as well as the address data. So here we are going to read the CSV file correspondingly to get the nodes and address data. And then we need to read the nodes features and convert the nodes features to a PyTorch tensor. So here, the only nodes feature pertaining to the age. So therefore, we are going to first convert the data frame column age to a NumPy array, and then convert that to a PyTorch tensor. And similarly, we also need to read the nodes labels and convert them to a PyTorch long tensor. The nodes labels are stored in the data frame column club. So we first convert it to a categorical variable and then to a NumPy array, and further converted that to a PyTorch tensor. And specifically, we are going to use the long tensor format. And we can also read the edge features and convert them to a PyTorch tensor as well. And the only edge feature we have is the weight of the edges, and we can read that from the data frame, edge data, convert that to a NumPy array, and then further convert that to a PyTorch tensor. Here we read the sources and convert them to a PyTorch tensor. So the sources are the nodes that send the message. We call it edge source. And similarly, we can read the destinations and convert them to a PyTorch tensor. And the destinations are the nodes that receive the message. And we'll call them edge destination. So if your dataset is a node classification dataset, then you will need to assign masks indicating whether a node belongs to a training or validation or test set. So here is how we split the nodes into the training, validation, and the test set. First, we get a total number of nodes in the graph, and then we can decide what percentage of the data we are going to send to the training data. And based on the percentage, we are going to set the number of nodes, which is just the integer of all the nodes multiplied by the fraction of nodes you want to send as the training set. And similarly, you can define the number of validation nodes. And after that, we can create the masks for train, validation, and the test set. First, we create the train mask, validation mask, and a task mask, filling the corresponding PyTorch tensor with zeros. And then we can create the tree mask by providing the number of train sample we want to have in the train set. And similarly, we can also create a validation mask and a task mask by denoting their corresponding sample size. After that, a common practice is to standardize the node features so that it helps the model converge. We are going to utilize the scikit-learn standard scalar to do that. First, we initiate the standard scalar, and then we fit the scalar we specified using only the node features in the train set. And after that, we can perform the transformation using what we learned from the train set on the entire data sets. And after that, we need to convert the standardized nodes features into a PyTorch with data type of float32 for modeling purpose. Now we are ready to define the graph by providing the source nodes, destination nodes, and the total number of nodes in the graph. We use the DGL graph function to do that. We provide the edge source and edge destination in the tuple, and then we also provide the total number of nodes in the graph. Since we have created the graph, we'll be able to assign the standardized nodes features to the graph. Here we call them feet, denoting the node features, and we supply the standardized nodes features. And similarly, we can assign the node labels to the graph and assign the edge features to the graph as well. And finally, we need to add the train, validation, and test masks to the graph by just adding additional columns. We call them train mask, validation mask, and a task mask. And now we can define the getItem method, which is very simple because here we only have a single graph. So getItem is just return the graph itself. And we also need to define the length method. Here, the length method is very simple because we only have a single graph. So therefore, we return a value of 1. After we define the customized DGL dataset, we can initiate the customized dataset by just calling the Karate Club dataset name and then provide the preferable split of the train, validation, and the test set. So here we split 60% of data to the train set and another 20% to the validation set, and finally the remaining 20% to the test set. And now we can take a look of the created data set by specifying graph equals dataset 0 because we have a single graph here. As you can see, when we print the graph, the corresponding graph schemes is presented here. So let's recap. A DGL graph can store node features as well as edge features into dictionary-like attributes called nData and eData. In the customized dataset, the graph contains the following features. We have the train mask, validation mask, and test mask denoting using a Boolean tensor indicating whether a node belongs to the training or validation or test set respectively. We also have a label denoting the ground truth node category, either belonging to clap 1 or clap 0. And we have feed denoting the node features. Here is the standardized age, as well as weight, which is the edge features denoting the importance or strength of the ties. We can print the node features using the graph in-data command. We can also print the edge features using the graph e-data command. Now let's build a 3-layer graph convolutional network or GCN model. And each layer will compute new node representations by aggregating neighborhood information. So we'll utilize the graph conv denoting the graph convolutional network layer. And we'll also, from Torch, we'll bring the NN method as well as the functional method. Here, we build a customized layer, and it is a child of the NN module. And that's defined the constructor. The constructor takes 3 arguments: the input features, the output, the hidden features, as well as the total number of classes. And we inherit from the parent NN module using the super method. And we define the first GNN layer as using the graph conv layer, and we specify the input features and intermediate or hidden feature size. And we define the second GNN layer in a similar fashion, but making sure that the output feature of H feeds must be equal to the input feature of the second GNN layer, which is also the H feeds. And we decide to use the same number of layers as output for the second GNN layer, and linking that to the last GNN layer, which has the same input size, but then the output size would be just the number of classes we want to predict. Here, the number of classes equals 2 because there are 2 classes we want to make the prediction. And then let's define the forward method. In the forward method, we only need to supply the graph we want to serve as the input to the model, as well as the number of input features. And we feed the graph and node features to the first GNN layer, denoted here. And then we can apply the ReLU activation function on the intermediate output. And then we feed the intermediate output to the second GNN layer. And we apply the ReLU activation function again on the intermediate output. And finally, we feed the input to the third and last GNN layer. And then we return the output. Now we can create a model with the given dimensions. We'll name it, we'll initiate the model GCN. And here we provide the input dimension, namely the number of node features. And we also provide the output dimension. Here we define the hidden layer dimension, in fact, and we'll name it, we'll give a dimension of 16. But, well, this is arbitrary. You can use other dimensions as well. And finally, we specify the number of node classes. So here, because we are predicting 2 class membership, so therefore number of classes equals 2. After that, you can print the model to take a look at the architecture of the model. And now, since the model is initiated, you can define a trainer, basically creating a training loop using the PyTorch method. And in the training loop, you just need to provide a model and the number of epochs you want the model to run. Here, you define the optimizer. We are going to use the Atom optimizer. We specify a learning rate of 0.01. You want to keep track of the validation and the test accuracy, so therefore you create 2 accumulators. And here you get the node features label and also the train validation and the test masks from the graph data set. You just need to specify which columns in the graph data that serve as the features, labels, and the 3 masks. And now you can define the training loop. The training loop consists first a forward pass. You pass the graph as well as the features to the model. And then the output would be logits denoting the membership. And then based on the predicted logits, you can use the argmax function to get the corresponding predicted index denoting club membership. And then on the one hand, you have computed prediction. On the other hand, you also have the logits from the train set, which serve as the ground truth, the label in the train set as the ground truth. And now you can use the cross entropy loss, calculate the loss so that you can do the backpropagation later on, making very sure that you only compute the losses using data from the train set. And then you can also compute the corresponding accuracy in the train set, validation set, and the test set accordingly. And you may want to save the best validation accuracy and also the corresponding test accuracy. And remember to zero out the gradients every time you run through the loop so that you get the gradients automatically set to 0 after each iteration and backpropagation. And then you can do the backpropagation, calculating partial derivative of the loss function with regard to your parameter estimates. And then you can update your parameters using the gradients. And finally, you can choose to report results over different epochs. And here we are going to report the epoch value, the loss, the validation accuracy, and the best validation accuracy across all the epochs implemented, as well as the text accuracy as well. And here we are going to utilize the GPU for computation, making sure that you move both your graph as well as your model to the GPU so that the model can be executed using the GPU. And now you can initiate training. And here we train the model for 100 epochs, and we got 100% validation accuracy and also 100% of the test accuracy. But one caveat here is because we have a super small sample size, so therefore the training results are unstable. So if you run the program several times, sometimes you get very high validation accuracy, sometimes you get very low accuracy, possibly denoting that either the sample size is too small or maybe you are overfitting the model. That concludes a brief introduction to the GDL library that you can utilize to quickly prototype and run graph deep neural network. Thank you for your attention. I'll see you next time.